Okay, so anyway, good morning, everyone. So I'm in the Central Time area, so it's like 7:43, so in the morning, and it's not New York time. So my presentation topic will be a review on the material performance of functionalized CNT and the hydrogen bond, which is modified polymer nano composites. And so it's just a kind of review. So because some of my students work on the simulation, so this is just and I will talk about several things. For example, some background for the polymer nano composites and also the carbon nanotube, and why functionize, and why hydrogen bond, and how they impact to the material property, for example, mechanical, electrical, thermal, and other property, and with some of the carbon nanotube, for example, morphology, and some other parameters. So this is some of the outline for today's topic. First, they have some brief introduction and give some fundamental why functionize the carbon nanotube and hydrogen bonds, and also why the carbon nanotube need to be aligned in the material, in a polymer, and also quick review on the material performance of carbon nanotube modified nano composites. So on the electric property, thermal, mechanical, and other property, and have some additional discussion for the future work, and a quick summary. So first one, as we know, for the nano composites, it's similar to the regular composite material. So we have basically three different categories. For example, according to the matrix, you have a metal matrix, polymer matrix, and a ceramic matrix. So they can form a different name of nano composite material. And there's a question why we need a nano composite. So because we already have a regular composite material. So the difference is when we use a nano reinforcement, so they increase there's several advantages for the nano composite. For example, increase the electric breakdown strength for the polymer, and increase in the melting temperature, and some other capability, and increase the interaction surface with the matrix. And also we can make the multifunction. So this picture you can take a look, with the large particle, we call them micro particle, and with the nanoparticle, definitely the surface area per volume of the material, the particle will be increased dramatically. So that's the interaction between the matrix and reinforcement will be totally different. So my topic will just focus on the polymer nano composites. So for the ceramic or for the metallic matrix, we are just skip them. So first one, you can take a look at the smaller filler. What is difference? So we can see we have exceptional high surface to the volume ratio to reinforce, or to exceptionally high aspect ratio. Aspect ratio is usually defined as the length to the diameter. So for example, carbon nanotube or the fiber. And also there's a small distance between the fillers. And for the mechanical property, of course, you increase the ductility, but without decrease the strength. And of course, when you have a nanoparticle, you can increase the scratching resistance. So that's you can use for the improve the wear, and so coating, So, and also the optical property will be changed. for example, transparency. So, and this is like a picture. You can see the dimension or the time scale. So that's will be different, described by the nano composites. For example, if you think about layered composites, you can just view as a macro scale. But of course, when you have a fiber, for example, reinforcement, maybe it's anisotropic. If you have a short fiber, very little tiny fiber, maybe in the macro scale, you can view as isotropic. And if you look at the particle cluster, so you can build your model in terms of micro scale. But if you look at the interface and how the particle or the reinforcement influence the matrix, so maybe you can use the nanoscale. So that's also the scale down to the several to tens of a nanometer. But if you look at the like electronic or atomic level of structure, absolutely you can even down to the smaller scale. For example, if you're talking about bonding or the immobilization, so that's all about the even the smaller scale. So that's in the atomic, scale. And also, there's a lot of application for the nanocomposite in terms of its exceptional mechanical, thermal, electrical, or other property. So I'm not going to list, for example, you can use for the automobile external interior panels, and also the structure panels, the building sectors, especially in the aerospace, industrial, so on the electrical device, packaging for the food, a lot of, and also reinforce, we know the matrix for the polymer, there's several different matrix. For example, you have elastomer and you have thermosets, because thermosets are usually applied to the electrical device, or the thermoplastic, you can inject, you can melt, you can remelt, so that's different. And with the in this topic, we'll focus on the carbon nanotube, So that's in that case, we were looking into the aspiration for the carbon nanotube. And of course, we have like volume percent, usually we call the loading, and weight percent, so there's a lot of things, and quality, So this is the filler, and usually the filler can divided into different category. For example, clay, you have a carbon family, you have a lot of carbon family. In the carbon family, you have a fluorines, you have a graphene, you have a nano fillers, and also carbon nanotube. So many, so they just list a few. And you have organic fillers, you have inorganic fillers. So, but we will just focus on the carbon nanotube because this area is so big, Carbon nanotube was discovered in 1991, and by a Japanese, his last name is Iijima, and work for the NEC research lab. So this is a typical single wall carbon nanotube, everybody knows. So, and usually for the carbon nanotube, we have a different name. For example, we have single wall carbon nanotube, we have a double wall, triple wall, we have a multi-wall carbon nanotube. So like 10 years ago, I wrote a chapter for the mechanical property of carbon nanotube and graphene. And the editor was Iijima, so I contribute to mechanical property for the filler. The reason is because my background is mechanical engineering, so I like to work on the mechanical engineering. But of course, this is no limited to just mechanical. So there's carbon nanotube. They have a lot of additional property, very unique. For example, electrical, thermal, and also like other property, So this is a table for the carbon nanotube. If you look at the We just pick the steel, 4340, and the tensor strength. So that's and also tensor modular. Tensor modular means Young's modular. Usually, because fiber, you only can do the tensor and the density. If you compare with the carbon nanotube, that's exceptional high. You see the tensor strength will be 30 times higher, and Young's modular will be several times higher, and the density, of course, will be like 4 times less, lower. So that's the reason. If we can mix up with matrix, we can much improve the performance of the entire nanocomposites. So this is a kind of family of nanocomposite, nanotube. For example, you have fluorines, you have different fluorines, you have a single word, you have a multi-word, and also you have complete the carbon nanotube, and also you can have without the half spherical end cover, so that's like this one, and this is another picture. So, and for the carbon nanotube, so usually we take the single word carbon nanotube to define its difference in terms of the wires. For example, we have so horizontal. This one is armchair. So you can see armchair. We have a two vector to define the rolling of the like a graphene, into the carbon nanotube. And another one you can see. This is another one. So that's a zigzag we call it. And between we call the coil carbon nanotube. That's the first one is the armchair. Second one is zigzag, and between the angles, so that's the we call the coil carbon nanotube. But each one they have different properties. So when we talk about, so for example, like this one, sometimes the carbon nanotube can be the metallic, and sometimes can be semiconductor. The reason is because if you have different angle rolling, so the connection of the energy state, so usually we know if you're in the chemistry background, you know the like low mono, low more homo, the highest occupied, lowest occupied, highest occupied. The orbital, so that's sometimes the orbital is not connected, so that's performs like the semiconductor. If this is connected, so that's electron can be easily transferred from one atom to another one. So that's perform like a metallic. So it's depend on the rolling angle. So this is some of the property for the mechanical property for the carbon nanotube. As you can see, the first one is a single word nanotube, armchair, and zigzag, and compare with like a stainless steel. So you can see, even for the carbon nanotube, sometimes they can probably can be ranged from lower to higher. So it's not just one number. So most of the number it's getting from like the simulation, and usually the small scales doing the experiment is very hard, and reliability or accuracy of the testing is sometimes questionable, or sometimes large deviation you can imagine. So, for example, for the thermal property of a carbon nanotube, sometimes the single word carbon nanotube can have like as high as 3,500 watt per meter per Kelvin. And if you compare with the good conductor like copper, so that's almost close to 10 times higher. You can imagine, so that's quite amazing. And also, if you compare the single word carbon nanotube itself, in the longitudinal axial direction or the lateral direction, so that's quite different. You can see, in the radial, so that's the lateral direction. So the conduction will only have 1.52 compared with like as high as 3,500. So that's totally different. So that's almost like insulator, you can imagine. You know. So that's the carbon nanotube is anisotropic material and quite anisotropic along the actual direction or the lateral direction. So this is the one picture you can imagine. You know, so the nano composite material, so they were affected by many parameters from the carbon nanotube. For example, first one is dispersion of a carbon nanotube. The reason is because carbon nanotube is low solubility. And if you load a lot of carbon nanotube inside the polymer, so the dispersion will be bad. So it's not very uniform distributed inside the polymer. So that's one thing we need to solve the dispersion. So how can we make the dispersion well and uniform? The second one is if you load the different amount of carbon nanotube will be, influence different. For example, in this case, electrical conductivity. You see, this we call the threshold value. So that's like a turning point from the lower electric conductivity to the high electric conductivity. It's similar to the, if you remember the glass transition temperature. So that's similar, So, or if you look at the mechanical property, we have another one is transition from, for example, brittle material to the ductile material. We have also a transition period time, the percentage or some critical value. It's similar. So that's the loading amount. And another one is, of course, this is a structure of a carbon nanotube. For example, you have a single wall, double wall, multi-wall, and you have a different quality. For example, you have armchairs, zigzag, and also aspiration. So the length of a carbon nanotube to the radius will be also influenced. And of course, for the matrix, what type of polymer. So many factors will influence the performance of carbon nanotube modified nano composites, you can imagine. So we won't be able to talk too much. For example, this is just one simple picture for the dispersion. How the carbon nanotube eventually will disperse, so into the polymer and with well uniformity. So next we need to talk about how we do this. So one thing is we make because the carbon nanotube it's low solubility in the polymer, in most of polymer. So we need to make the carbon nanotube either the surface functionalized so that they can be easily well contact with the polymer matrix so that they can dissolve into the the polymer matrix. So we need to select some solvent, and also we can use so for the functionalization. So we have a different category. For example, one is a covalent method. Covalent, you can imagine, covalent will be very strong bonded. Sometimes they can damage the surface of the carbon nanotube because the bonding is strong and attraction, repulsive is also very strong. And another one is the non-covalent method. Non-covalent method, so the bonding will be very weak, and but they will not damage or modify the surface of the carbon nanotube. So this is good, bad. So this different way. So so this is another way, if we use a covalent bonding for the functionalization, so you can imagine, so sometimes they can make the bonding on the side of the carbon nanotube wall, or maybe they can break the end, so bond on the end. So that's another one. And if we use a non-covalent bonding for the functionalization method, you can see mostly is on the surface. You can like overlap the carbon nanotube, make this longer, or you can make the carbon nanotube well, the melted into the matrix. So that's a different way. So hydrogen bond, we know this is a very weak bonding, but usually is higher than the von der Waals interaction, and they have certain strengths, and they can bond, and they can improve the solubility and bond the carbon nanotube with carbon nanotube. So they have multiple applications. For example, this is several example to form the carbon nanotube for the hydrogen bonds. For example, the first one is the water molecule. Because of the symmetric of the electron cloud, so they can form the positive, negative charge center will be deviate, so they can bond together. So that's they have a different, so in case you have this like water, or this is the water, ammonia, or fluoride, so that's another. So they all can easily form the hydrogen bond. And also another property, another question is if we can align the carbon nanotube in the matrix, so that you can imagine in the alignment direction, the performance of the nano composite will be extremely well outstanding. So that's sometimes we only use the directional performance. We are not using all the direction. So in that case, alignment is very important. So this is, for the alignment, we have several ways. For example, we can use a mechanical way. We can use like electromagnetic way to make the fiber to be aligned. So this is just one example. We use the electrical field to make the alignment. So if the carbon nanotube can be, well dissolved into the matrix. So in that case, you apply, you make the functionalize on the surface of the carbon nanotube to make it like magnetized or the electrolyzed. So when you apply an electric field or the magnetic field, so they can be generate electric field and a magnetic field over the entire polymer, so they can turn, change the direction. So you can see the last one is they change the direction, and so in the alignment direction, so the property will be totally different. This is just one of the example. You can see if you have aligned the fiber, and the performance will be way high. This is just for the thermal conductivity. You can imagine. So even for the electrical, for the mechanical, so that will be totally different. But this is only for the alignment direction. So first one, we have some quick review for the material performance. First, we just look at the electric property. So you can see, so this is on the bottom. We have like two carbon nanotube. After functionalized, and maybe they can overlap, so that electron can be transferred through one carbon nanotube to another carbon nanotube because it's connected. So we call this is the electron pathway. If you generate a lot of such a pathway, you can imagine when we test the electrical property, so the conductivity will be much, much improved. So that's the kind of the strategy. And this is so many data, mostly from the experimental result from the research from literature. And so you can see, so for example, we have functionalized, we have some, the result, if you look at the electrical conductivity will be much, much higher. So, sometimes the measurement is not electric conductivity, so maybe it's electric resistance, and resistance will be reduced. So that's the, And the second one is thermal property. It's similar. I use the same figure. You can imagine if we can overlap or connect the multiple carbon nanotube, so that's they can form the phonon, the transfer the path. So we call the heat flow. So that's you can improve the thermal conductivity. It's similar way, when you apply a heat source on one end, so the other end, maybe you apply some heat sink. So that's cooling area. So that's the temperature will be transferred from a high to the low, and then will be increase the thermal conductivity. So that's the, sometimes we need to use this design. So this is some of the data you can imagine, so for example, when you have a functionalized carbon nanotube, sometimes the thermal conductivity can improve like 163%, or sometimes can reach 500 even more percent. So that's a lot, so that's give you some, for example, this one. So the thermal conductivity can, with aligned carbon nanotube, you can increase the conductivity to 681 times. So that's extremely high. So that's the reason. But usually the loading, if you look at the last column, loading is very low. So because the nano filler usually the loading should be and also the mechanical property, it's similar, so when you have a carbon nanotube functionalized, can be overlapped, so the stress can be transferred. So that's you can improve the strength or the modular, because usually matrix cannot take the stress, and usually the strength or the Young's modular will be determined by the filler. So that's the reason, you improve the stress transferring. So that will be, so there's a lot of data. So we just take a look, for example, if you have functionalized, the carbon nanotube can be improved, the elastic modular 79%, or tensor strength 47%. And sometimes even can be higher, so you can see 9 times the Young's model improved, and tensor strength also 9 times, improved, or sometimes the ductility, or the, so that's a lot of, so there's so many, so this is all the data should be carefully read. There's a lot of data. And the other property, for example, transparent. So they can make the transparent to be as high as sometimes you can use in the monitor or something, and anti-corrosion and the protectivity, the efficiency can be improved very high. So I'm just quickly, and additional discussion, because all the results we saw is about the experiment, and also if you carefully read the results, because so many parameter or factor influence the performance, so it's hard to compare, in the graph. The reason is because, for example, the fabrication process is different condition. So how can you put them together? So it's not the same thing. So in that case, in the future, maybe we can do in some specific comparison under the same condition and with the modeling, computer modeling, so that we can easily compare the result, how the performance changing and improve them. So we can plot the graph easily. So we just fix all the other parameter and the factor the same. Maybe change one or two parameter and factor so that we can plot the result in the figure. So that's in the future. And for the simulation, of course, we have so many ways to do the simulation. The first one is quantum mechanics, emulation. So which is you can do very accurate, but the model should be very small. So that's limited our capability. And the second one right now is very popular for the molecular dynamics simulation. So right now, my student is focused on this one because the molecular dynamics simulation, right now we can do the simulation up to like 1 million of atom, which is still small, but compared with the quantum mechanics will be much better. But like a finite element analysis is impossible because this macro scale, you won't be able to see the details in the nano scale. So maybe molecular dynamics is the most feasible. We can adopt in the next step to provide the more details for the, how the factor influence the nanocomposite. So because the molecular dynamics simulation, you can see they can include a lot of details from the molecular. For example, you can include the stretching, bonding, the bending, angle bending, and the rotation, and a lot of the interaction between the inside the molecule. So that's the and so here is the summary. So we quickly review the research in the recent 20 decades in the area, including the carbon nanotube modified with high electrical thermal conductivity and erosion, corrosion resistant nanostructured composites, and with chemically functionalized the carbon nanotube incorporating with hydrogen bond. And also including the directional alignment in the polymer matrix for the reinforcement. And of course, in the future, so we have to consider the computer modeling for, looking into the details, the effect of the influence of property of the parameter and factor on the material property. So this is the purpose is for the effective design, the new or novel material in the future. So thanks for your time and maybe question.
I have a question, if I may ask, Dr. Zhuang. That was a very interesting talk. I enjoyed. So the part that you mentioned, the functionalization for getting more interactions between the nanotubes. So how do you deal with the making homogeneous solution for a composite material? So I assume that if you functionalize them before, they start stacking together, and then making a composite would be more complicated. Could you please comment on that?
Yeah, this is another huge area because solvent, there's a lot of different solvents, and also it depends on what kind of the matrix polymer you use. So there's huge literature. The people use a different solvent, and yeah, it's a case by case. Yeah. Yeah, it's
Thank
very
you.
hard to have just just a few, so yeah,
Thank you.
people develop a lot of different solvent. Yeah, thank you.
Thank you, Professor Zhen, for your delighting presentation. Maybe we have a question. Yeah, Mrs. Margaret Cruz has a question. Mary, which sector is seeing the faster adoption of nanocomposite? Is it automobile sector or aviation or consumer or any other?
Which sector? So can you repeat? Sorry, I missed the point you asked for.
Which sector is seeing the faster adoption of nanocomposite? Is it automobile sector or aviation or consumer or any other? Proposition, could you hear me?
Yes. So I think that's your question, right?
Yeah, Mr. Margaret Cruz asked.
Right now, I think mostly is for the polymer carbon family nanocomposites. The reason is because a lot of people, develop carbon family filler, which make the application is very broad. And usually the application for the like a metallic or the like a ceramic matrix is very less, usually used in the like coating and thin film and in the aerospace something. So but for the majority application usually is polymer matrix and the carbon family as a filler. So because carbon nanotube right now the price is drop quite a lot. So many years ago, so I remember it's like $100 for just 1 gram. So that's maybe 10 years ago, if I remember correctly. But right now is much cheaper. If you go to the online, you can buy the commercialized very cheaper. So a lot of people develop the polymer because the polymer is very cheap. So and very easy to make the well dispersion of nanofiller. So that's the kind of reason. So I think so. Yeah. Maybe there's some other. It depends on the application. So. I don't know if I answer your question.
I guess we get that. Thank you, Professor Jung, for your, yes, I think.
Yeah.
And thank you
for
for
everyone
your
for the time.
presentation. Best wish for you.